Hello everyone, and welcome to our presentation. Today, we're going to explore the fascinating world of gas turbines. The title of our talk is Gas Turbine Basic Principle. We'll be looking at how these incredible machines work and their fundamental concepts. Over the next few slides, I'll guide you through the key ideas and mechanisms behind gas turbines. I'm excited to share this knowledge with you. Let's get started. Let's dive into the open Brayton cycle, also known as the simple cycle. This cycle involves four main process steps. First, we have compression, where the air is compressed to a higher pressure. Then comes combustion, where fuel is burned to add energy to the system. Next is expansion, where the hot gases expand through a turbine to produce work. Finally, there's exhaust, where the gases are expelled from the cycle. Now, when it comes to efficiency, there's a handy formula to estimate it. Efficiency is approximately equal to 1 minus the reciprocal of the pressure ratio raised to the power of 0.286. For example, if the pressure ratio is 10, the efficiency comes out to about 48%. It's also important to note that there are standards guiding these cycles, like ASME PTC 22 and ISO 3977, which ensure consistency and safety across different implementations. Understanding this simple cycle gives us a solid foundation for exploring more complex gas turbine systems later on. Let's take a closer look at the Combined Cycle Power Plant, or CCPP for short. The main idea here is that it combines a gas turbine, a heat recovery steam generator, and a steam turbine to generate electricity more efficiently. Essentially, the waste heat from the gas turbine is used to produce steam, which then drives a steam turbine to generate additional power. This synergy helps maximize overall efficiency. To give you a quick idea of how the efficiency is calculated, there's a simple formula. Eta equals the efficiency of the gas turbine, GT, plus the efficiency of the steam turbine, SD, multiplied by the remaining potential, which is 1 minus GT. For example, if the gas turbine operates at 35% efficiency, and the steam turbine at 30%, the combined efficiency would be about 55%. It's also important to note that these systems adhere to recognized standards like IEC 60045, ISO 2314, and ASME PTC 4, which ensure safety, reliability, and performance consistency across different implementations. Overall, the CCPP is a remarkable example of how integrating different technologies can lead to more sustainable and efficient power generation. Let's take a closer look at cogeneration, also known as CHP, which stands for Combined Heat and Power. Essentially, this process uses a single fuel source to generate both electricity and useful heat simultaneously. It's a highly efficient way to maximize energy output from the fuel we use. The key idea here is that instead of wasting the heat that's usually a byproduct in electricity generation, cogeneration captures and utilizes it for other purposes, like heating buildings or industrial processes. This significantly improves overall efficiency. Speaking of efficiency, we often measure it with this simple formula. Eta equals the sum of the electrical and heat efficiencies divided by the fuel input. For example, if a system produces 35% electrical efficiency and 40% heat efficiency, the combined efficiency would be 75%. That's a big improvement compared to traditional methods. It's also important to mention that there are standards guiding cogeneration systems, such as ISO 11086 and ASME PTC 46. These standards ensure that systems are designed, operated, and evaluated consistently for safety, reliability, and performance. Overall, cogeneration is a key technology in our journey toward more sustainable and efficient energy systems, aligning perfectly with our theme of optimizing energy use and reducing waste. Let's take a closer look at the different types of gas turbine designs. First up is the single-shaft GT. These turbines are known for their simplicity, making them ideal for many applications. They feature a single shaft that connects the compressor and turbine, resulting in a compact design that is both efficient and easier to maintain. Next, we have the two-shaft GT. Here, the power turbine is separate from the gas generator, which allows for greater flexibility in operation. This design is often used in situations where varying power outputs are needed, thanks to its ability to operate efficiently across different conditions. Moving on to the aeroderivative GT. These turbines are lightweight and designed for rapid startup, making them perfect for applications where quick response times are crucial. They are adapted from aircraft engines, which is why they are so fast to deploy and highly mobile. Then there's the heavy-duty GT. These turbines are built for continuous, reliable operation at high loads, making them ideal for baseload power generation. They are robust, durable, and designed to run steadily over long periods. Lastly, it's important to remember that these designs adhere to strict standards like API 616, API 617, and ASME B133. These standards ensure safety, reliability, and performance across different turbine types and applications. Understanding these different design types helps us select the right turbine for each specific energy need, aligning with our overall goal of efficient and reliable power generation. Now, let's explore how this system integrates with reverse osmosis desalination. The key idea here is that the power generated by the turbine is used to drive high-pressure RO pumps, which are essential for the desalination process. Additionally, the exhaust heat from the turbine can be used to preheat the RO feedwater, making the process more energy efficient. To give you a sense of scale, roughly 1 cubic meter of RO produced requires about 3 kilowatt-hours of energy. So, for a plant with a capacity of 500 megawatts, we could potentially produce around 150,000 cubic meters of desalinated water per day. It's also important to note that this integration aligns with recognized standards like AWWA B100 and ISO 14001, ensuring that the system meets quality and environmental management guidelines. Overall, this approach demonstrates a sustainable and efficient way to combine power generation with water desalination, supporting our broader goals of resource efficiency and environmental responsibility. Let's take a closer look at the Jubail Power and Water Plant in Saudi Arabia as an example. This plant uses a combined cycle configuration along with reverse osmosis desalination, which is quite efficient for both power and water production. It generates about 1,000 megawatts of electrical power, enough to support a large regional demand. In terms of water, it produces approximately 300,000 cubic meters per day, providing essential freshwater through desalination. What really stands out here is the overall efficiency, which is around 55%. When we consider the combined efficiency, including the combined heat and power, or CHP, it jumps to about 75%. That's a significant indicator of how effectively this plant utilizes fuel to produce both electricity and water. Additionally, this plant adheres to international standards such as IEC 60045, ISO 2314, API 616, and AWWA. These standards ensure safety, reliability, and quality in operations, which are critical in such large-scale infrastructure. This example underscores the importance of integrated systems and high efficiency in modern power and water plants, key themes in our overall discussion of sustainable and effective resource management. Let's wrap up with a quick summary of the key formulas we've discussed. First, for gas turbines, the efficiency is calculated as the power output divided by the heat input, typically ranging from about 30 to 40%. This highlights how much of the fuel energy is converted into useful power. Moving on to the Brayton cycle, the efficiency depends on the pressure ratio, R, and follows the formula 1-1 divided by R raised to the power of 0.286, with efficiencies generally between 35 and 48%. Next, the combined cycle efficiency combines both gas turbines and steam turbines, and it's calculated as the efficiency of the gas turbine plus the remaining energy converted by the steam turbine, often reaching 50 to 60%. And finally, for combined heat and power, or CHP systems, the efficiency is quite impressive. It's the total electrical and heat output divided by the fuel input, often between 70 and 80%. These formulas are essential because they help us understand how different power systems perform and how we can optimize energy use across various applications, tying back to our overall goal of improving efficiency and sustainability in energy generation.